Welcome to the Alpha Training and Consulting's online training program. Today's module is entitled Response Surface Methodology module. The purpose of this module is to define the Response Surface Methodology, or RSM, to discuss the Steepest Ascent methodology, to discuss the Central Composite Design, or CCD, and to discuss other designs that are applicable to RSM, or Response Surface Methodology. What is response surface methodology? Well, or RSM? Well, it is a sequential procedure that couples the concepts of experimental design, DOE, and optimization theory. The purpose of the methodology is to determine the optimum operating conditions for a given set of process variables. So it's considered a more advanced topic in the world of design of experiments. This is accomplished by modeling the functional relationship between a set of independent variables and the response variable using experimental design techniques. And I'm going to go back here and remember, this is a sequential procedure to make all this happen, to determine the optimum operating conditions. Well, that sequential procedure is listed right here. And we're first going to talk a little bit about screening DOE. I'm not going to talk a lot about that because I've already talked about that in previous discussions. So we've already covered the gist of this, but we're going to refer back to it as this is the first step in this sequential procedure. So screening DOE, you could also do fractional DOE or full factorials are also acceptable in this first step. And the reason for doing that is you're looking to identify important factors. Then you fit the first order regression. An outcome of a DOE is a mathematical equation, and so you'll come up with that equation. We call that a first order equation because it has no squared units in there. We'll talk about that in greater depth later. Calculate gradient, large coefficients that are statistically significant. Do the steepest ascent using those statistically significant coefficients. And when improvement stops, that's the end of this sequential step. Then we go into response surface DOE, such as CCD, Central Composite Design, and Box Behnken. We cover a couple others also. And then we fit to a quadratic model, and this equation will then have squared terms in it, and find the optimum. So this is the sequential procedure that I'm talking about. Okay. And to do this, you have to first start visualizing things in 3 dimensions, or else this isn't going to work very well for you. So what I've done here is a 2x3 full factorial design, and it looks like this. And here I have all the runs. We've discussed this earlier in another module, a full factorial 2x3. Here it is. And run number 1 is minus, minus, minus. Well, on this cube, minus, minus, minus is this corner right here. So we get a response variable when we run number 1. A 2x3 creates a cube. All right. And number 2 is plus, minus, minus. So here's 2 plus, minus, minus. We run the experiment at those settings, get a response. That value of that response lies right here on this cube. Not all designs create a cube. That's why I chose the 2x3 full factorial, because it creates a cube on what I call design envelope, informational envelope, operational envelope. Has a few names there, like most things do. But you have to visualize that this is the information envelope, and when I run a 2x3 design, I can pretty much predict anything within this cube. And so that's why we call it the envelope, the information envelope, the design envelope, or the operational envelope is another word you can use there. And we can predict almost anything within here with a fair amount of confidence if we do it correctly. And so you have to start visualizing this envelope here. And every corner of this cube is in relationship to one of these runs. And you can see the planes on here also. I'm not going to go over all the planes and everything right now. Well, maybe I will. Here's the C plane. it's on the sides. The B planes are on the top, at least the way we have these referenced. And the A planes are, the A planes are on the side. These C planes are on the front and back. And so those are the planes that give us boundaries to our informational envelope. What else can I tell you about this? This is where you usually start in this procedure is you run your full factorial design, for example, it would be the case here, and identify the important factors. And this is what it looks like in three-dimensional space. So we're going to have to start thinking about three-dimensional space. Then we have these two-way interactions. The BC interaction creates two planes there. AB creates planes this way. AC, you can see those planes and where they're at. And the three-way interaction have these triangles in there. But when you put all these together, there's a lot of space where you have planes that you can predict anything within those planes. And there's small gaps in between those planes, but you can easily interpolate between those planes. So in other words, you can pretty much predict anything that happens within this design envelope with this DOE. And some industries say, hey, create your design envelope and make it as big as you want. And if you can make changes within the design envelope and you won't have to revalidate the process. They say that in the pharmaceutical industry. I'm sure they say it in other industries as well. So they may do this cube here, then they'll add another cube over here and another one over there and some on top, so that you can make a lot of changes in this process without having to revalidate. So there's a good reason for constantly growing your informational envelope. Okay, so hopefully that was helpful. Now you have to remember just the nature of things. The further apart these are, the less likely those planes will be flat. See, I'm assuming these planes are flat and everything is linear. If it is, I can predict anything within this cube. If it's not linear, then I'm going to have some error in the design envelope, and you don't want that. So you always have to check, do a test to see if these planes are flat. And the sides of this cube are flat. And the further apart you make the plus and minus 1 in your settings, in other words, the bigger you make this cube, the less likely it is to be flat. And the way I explain that is with this polynomial. You may think, oh, this is not linear. Well, it is if you break it up. If you go from here to here, it's pretty linear. If you go from here to here, it's pretty linear. If you go from here to here, it's linear. You see what I'm saying? If you break it apart, but if you make it too big, it won't be linear. And that's the problem you have in these DOEs. You don't want to make them so big, the design envelope on your first run anyway, to where you give too much space and this plane will eventually break down. It won't be flat. Now I'm going to tell you how to deal with this if it's not flat. And you run center points in all of these to prove linearity. So there's ways to validate linearity, or verify, probably should say. Okay. And so that's what this is for, is to remind you that the bigger you make this cube, the less likely it is to be linear, flat planes. Okay, let's look at some other informational envelopes so that you can start seeing in 3 dimensions anyway. It goes way beyond 3 dimensions, but it gets too difficult to draw, okay? So this cube that we talked about here was for full factorial design, DOE. And all the interactions and everything fill that thing up pretty good where you really understand what goes on in that informational envelope. But if you run a screening design where you throw a lot of the runs out, most of them out, you end up with this shape, which is called an octahedron. Okay, And that's what you get. But inside this octahedron, since you haven't run any interactions or anything, you're just assuming linearity all through here without as much data to back it up. But it still works, but you have to check it to see if everything's flat. Why do I bring this up? I just wanted to show you the shape of another design envelope. Every DOE is going to have its own shape of design envelope, and you need to be aware of those. So you can read more about this, but that's why I put this up here. I just wanted you to see another example. Okay, illustration of RSM, response surface methodology concept. Let's assume the functional relationship between a set of independent variables and response variables can be mathematically as given y, an dependent variable, is the product of multiple x's. That's what that's saying. This relationship establishes the response surface where the actual analysis is performed. So here I have temperature, pressure, and yield. And I can take any of these values, the temperature and pressure, and it will go up here and give me the value from those two variables on this response surface. So that's what we're trying to do. How do you create this surface? Mathematically, how do you go about creating this? What's the methodology? And that's really the objective of this module, is to create this. And then to find the maximum, the highest point, or the minimum. That's the same type of thing. You can either find the maximum or you can find the minimum, what's ever more important. If you're looking at standard deviation, you usually want to minimize it, so you'll be going the other direction, looking for the bottom. Okay, but this one we're trying to find the maximum, so we're looking for this point right here within the kind of the design envelope. Where does that lie? And so that's what we're going to show you how to do. All right, illustration of RSM concept. A corresponding contour plot is usually given to the response surface plot to show the conditions, independent variable settings, along with the response dependent variables location based on analysis. So what we do in this module is we show you how to find it where the slope is 0 here. That means you've reached the peak and all the slopes are 0. And that's the optimal point. And then we give you what the settings need to be for, in this case, the pressure and temperature to get the ultimate yield. And so that's what this is all about. Illustration of the RSM concept. The surface from the functional relationship is searched systematically using optimization techniques such as method of steepest ascent or method of steepest descent, to identify or locate the optimum point on the surface as well as the corresponding conditions for the independent variables. Once the optimum point is approximated, a new response is then modeled and the optimum response for the new response surface is sought. This procedure continues until no further gain in the response variable is evident. So, you kind of poke around in this curve, to find out where that optimum is. And again, we're going to show you the methodology to reach that goal with as few data points as reasonably possible, and still give you good confidence that you can predict things. Methods of steepest ascent or descent. A method used to systematically climb a response surface, specific step size to seek out an optimum point. It applies to searching for a maximum point on the response surface. By contrast, the method of steepest descent is used to systematically descending on a response surface to seek out an optimum point and is applied to searching for a minimum point on the surface. Okay, so you're climbing or you're descending. You can choose whichever one. If you're trying to minimize something, you go with this one. If it's for yield, you want to optimize. Okay, standard deviation is one where you want to go through the descent and find the lowest peak. Where is the lowest standard deviation found, for example? The direction of the search, steepest ascent, is normal to the contour lines. See figure A on the next slide, and it's taken through the center of the operating region on figure B, next slide. So let's look at that. So this is how it all works. This is step one down here. And you do a DOE. This one is a 2x3 full factorial. How do I know? Because it creates a cube. Okay. And then once you get this done, you find out that, oh, look at the mathematical equation that's a byproduct from this experiment. This is the bigger coefficient, or usually you take all the coefficients that are statistically significant and you start increasing them in such a way that the response variable increases. Okay, and you keep increasing them a little bit at a time, a little bit at a time, and it keeps going up a hill. It keeps becoming bigger in this case because I'm trying to find the optimum by going up. And eventually it goes up, then it goes down. Well, right in this region then is where you experience, this is where you'll run your new experiment, and this is where we find the contour and everything. But we get close first. Again, find the most important variables to this process. Use those variables to run you up this slope. And when you reach the peak, you're in the basic area here. Then we're going to go into this area where this peaked out, and we're going to create that response surface. And that's where we're going to find our optimum. So step one, do the DOE. Could be a screening design, fractional factorial, or full factorial design. Either one is fine. And gives you your first order equation, which I'll talk about later. But from that equation that's a byproduct of this experiment, you increase your variables to increase your output if you want to go up until you have a positive slope. It keeps increasing, then it goes down. Okay, this is where, the optimum point is in here somewhere. Then we create a new envelope, information envelope here, and study that. That's where we create our contour in here to see where the actual peak is. So that's a summary of what we're going to go over, only we're going to go over it in pretty good detail to teach you specifically how to go about doing this. First, we have to understand first order equations and second order equations. This is a first order equation, y equals mx plus b type thing. There's no squared terms here. Because there's no squared terms here, it is just doing the flat planes. That's all it's doing. That's all a first order equation can do, is linearity stuff. If it has any curves, it's going to show up as an error. So that's your first order equation. That's what you're creating down here is your first order equation. And from your first order equation, you're doing that ascent or descent, whichever way you need to go. Okay, but that's step one, is creating this through a DOE. Then your second order equation, notice there's linear parts and there's also curvature parts, quadratic portions, if you will. See that x squared? That's what makes this a second order equation. And then this is the interactions, of course. Because when we perform this analysis up here, we look for curvature in here also. And we also do interactions over here as well. So the big outcome that you need down here is the first order equation, the first order equation. And then that second one up there, that's where we've taught you how to do this before in earlier modules. But this one, we're going to teach you how to do these x squared components to take into account the curvature that may be there. All right, with that being said, let's go ahead and go back to step one here. Step one, perform a screening experiment. Remember, it can be a fractional, can be a full factorial also. But mostly what you're doing it for is to get that first order equation. So a 2x2, a 2x3, fractional factorial, screening design, whatever you desire. Experiment identifies the important factors. And so let's use this as an example. Y equals 42 plus 6a plus 3b plus 1c. This is a first order equation. And you did that by creating this equation here. Now you can also have, plus a times b, which would be the interaction terms. It's not going to hurt anything. Okay, where A equals temperature, B equals pressure, and C equals speed, let's say. And the output is yield. The coefficients tell us how strongly each factor affects Y. Okay, these coefficients tell you how big of an impact it has on Y. Steepest ascent methodology, purpose, used when the objective is to maximize the response, maximize yield, minimize standard deviation. Examples: increase tensile strength, increase product yield, increase customer satisfaction, increase battery life, increase reliability, etc. These are all increase. I should have said decrease standard deviation, then we would have had ascending and descending. But the principle's the same whether you're ascending or descending. The idea is simple. Move from the current operating conditions. Where's the current operating conditions? I'm going to go back here. The current operating conditions are right here. That's what we're talking about. Current operating conditions. So the idea is simple. Move from the current operating condition in the direction that increases the response the fastest. So you're looking for the steepest ascent. Imagine standing on a mountain, you want to reach the highest peak. The steepest ascent path is the direction where the hill rises most rapidly. So that's what we're looking for. Going back to this diagram here, we're looking for the steepest ascent to get on top of the mountain. Okay, step 2. You may ignore small factors. I'm going to ignore it because this is I'm just trying to keep things simple to start with. Later on, I'm going to add everything in here. But for right now, I look at A as temperature, B as pressure, C as speed, and factor C contributes very little because it's 1 times C. So for right now, I'm going to get rid of that and just primarily work with A and B. 3, determine the gradient. The regression coefficients form the gradient vector. So we have a 6 and a 3. A 6 is the rise for temperature, and 3 is the rise for pressure, or the slopes. This is the direction of maximum improvement. Okay. So we're going to go up here, and we're just going to increase A and B incrementally and say, oh, it's giving us more yield, it's giving us more yield, it's giving us more yield. Oh no, now it's going down. Okay, the peak is right there. That's what we're looking for. But we're going to go in this direction at that magnitude. This is the direction of maximum improvement. So convert to practical step sizes. So this is 6 and 3, the coefficient 6 and 3. And I'm going to find, it's like finding the lowest common denominator, right? It's going to be 2 to 1 is what we're looking for. So if temperature changes in 10 degrees Fahrenheit increments, pressure changes in 5 because it's 2 to 1. If I'm going to increase this by 10, that's double there, then 1 must be 5 for my PSI. And that's the direction I'm going in those magnitudes of steps to go up that peak. Relative step ratio, possible movement. We're going to go temperature plus 20 degrees because this is 10, does 10 degree increments, but it's 2. So I'm going to make that 20, and I'm going to make this 10 because it's 2 to 1. And we're just going to repeat that over and over again like this here. We start out with 100 degrees Fahrenheit and 50 PSI. Then I'm going to increase temperature by 10 degrees, or 20 degrees, I'm sorry. 120 degrees, and I'm going to increase pressure by 10. So then I test at 120 and 60, 140 and 70, 160 and 80 PSI. Continue until the response no longer improves. Let me do an example. Let's say I do 100 degrees Fahrenheit and 50 PSI, and I'm at a yield of 90. Well, I want to improve it. So then I say, well, if it got better when I increased it, then that's good. So I go to 120 and 60. Oh, now my yield's at 95. So that's even better. And I keep doing that, incrementally doing that. I go from 101, 108, 112, 113. Oh no, look what happens. Boom, improvement stops and you start going down. So that's an indication that the peak is somewhere in there. That's what we're looking for right there. So the improved, and you can go back here to these coordinates and say what created that, and that will get you started in the right direction. The improvement has stopped. That means you've reached the neighborhood of the optimum. Now you perform another DOE, usually the central composite design, which we'll go over in great detail, by the way, or the Box Behnken Design, which we'll go over to a lesser degree, to model the curvature and locate the true optimum. And I'm going to be using this book from Montgomery. This is Douglas C. Montgomery, and he's a real brainchild at DOE. So we're going to use him in our journey here and some of the things he says in his DOE book. Determine the step of ascent, assuming it passes through blah, blah, blah. Montgomery says the path of steepest ascent is proportional to the signs and magnitudes of regression coefficients. Remember, we used the 6 and 3, those regression coefficients? That's what he says. That's what you should use to find the steepest ascent. Let me read that again. The path of steepest ascent is proportional to the signs and magnitudes of the regression coefficients. The following is a generalized logarithm for determining the path for k points. A. Choose a step size in one of the process variables, say change in xj. So this, when I say xj, it means the independent variable, and j means of the coefficient of greatest magnitude. So x of j in our case would be, let's go back here. X of j, 6a would be temperature. Temperature is j because it's the largest one. They call that j in his books. I will be the other coefficients, but they're not the greatest coefficients. Okay, so j has to do with just the largest coefficient. There it is right there. And change of x means how much you change. Remember, we changed 20 degrees temperature and 10 degrees pressure, I believe. Choose a step size in one of the process variables, say change in xj. Usually we would select the variable we know the most about, or we would select the variable that has the largest absolute regression coefficient, which we call beta j. The hat on top, by the way, is just what we've used data that we have to estimate that. All right, here we are at step B. The step size in the other variables is. Now, this gets rather complex. Once we do an example problem, trust me, it's not that bad, but just looking at it, it's rather difficult. The step size in the other variables. I want you to remember that word, other variables. So what's it talking about, other variables? Well, you have two variables here, two coefficients, beta I and beta j. Now let's go back and read the last paragraph here from Montgomery. Choose a step size in one of the process variables, and he's going to call that what? Change in x of j, and he's going to call the coefficient for this beta of j. That's where this comes from. This beta j and change in x of j is the largest coefficient, is what you'll find. Choose the step size in one of the process variables, and let's call it change in xj. Usually, we would select the variable we know the most about, or we would select the variables that has the largest absolute regression coefficient. And that's what we're going to do in our example, and we will call that largest absolute regression coefficient, beta sub j. So we have change in x of j. That's how much we're going to change it, and that's the coefficient. These are both of the largest coefficient. So let's go and look at it again. And so what are the other variables? Well, we call those beta I. Notice it's plural, variables. So let's go back and look at this. Well, it's right here. This is the largest variable. See that coefficient 6.5, this coefficient's 3, this coefficient's 1.5. So 0.5 or 6.5 is beta j. That's what this is right here. And we have to determine how much we're going to change it by. We haven't decided that yet. But that's for us to decide as the designer of the experiment, how much to change it as we change and see how things improve as we go up. That's what we're doing here. and the other variables is beta I. So 3.0 B, coefficient B, and 1.5 times C there, that's coefficient C. Both B and C are beta I's. They're the other variables. So that's what this equation's doing. Now we're going to go ahead and do some math so that you feel comfortable with this, because I want you to feel comfortable with this. Because I want you to feel comfortable running these experiments. And we have to take it a step at a time because there's a lot of steps in this process. So here we go. I broke it down. The constant of the equation is 82. The beta of A is 0.5, or 6.5, I'm sorry. And beta B is 3, and beta C is 1.5. So I wrote down all the coefficients, and the largest one is going to be beta J. And beta I is going to be 3.0, and beta I is also going to be 1.5C. Remember, it says other variables, plural here, so there's multiple ones you'll do here. Calculations. Multiple iterations, if you will. Okay, with that being said, let's move on to the next one. What is beta J? Montgomery uses J to identify the factor you choose as the reference variable, which is usually what? The largest coefficient. Typically, you select the factor having the largest absolute coefficient. In our example, factor A, coefficient is 6.5, factor B, 3.0, and C, 1.5. There we have all the coefficients. So this is the largest absolute value of this one. That's not negative, but it was. If it was, it would still be the largest one because it's the absolute value of. A has the largest coefficient, therefore J equals A. Okay, this beta J is going to use this coefficient right here, 6.5. So beta J is 6.5. Okay, now that we've established that, we have one of these three variables identified. Now let's look at the X one. Change in XJ. Now, look at Montgomery's equation. He writes, change in xi equals beta I divided by beta j divided by change in xj. Let's substitute numbers. Suppose we decide change in A equals 10 degrees Fahrenheit. Okay, fair enough. So that's what we've decided. That's what we're going to change. This is the authority of the designer of the experiment to make this decision. It's not something I pulled out in a book. We just decided let's do it 10 degrees at a time. Since beta A is 6.5, the largest coefficient, then 6.5 divided by 10 equals 0.65. So that's that part of the equation. That's the most difficult part of the equation right there. Beta J divided by change in xj is 6.5 divided by 10 is 0.65. So we have the denominator solved. Now we just have to put in the other coefficients here, which were what? 3 and 1.5. And we'll put those in and see what the change in x is for those. That's where we're headed. Notice Montgomery says, convert the change in xi from the coded variables to the natural variables. This is because the regression equation is almost always built on coded variables. That's the +1 and -1. We've already discussed this in previous modules. So you should feel comfortable representing the variables as high and low there with plus and -1, not actual engineering units. For example, factor A may be temperature, or the one we're looking at here, and the low, or -1, is 180 degrees Fahrenheit, and high is plus 10 degrees Fahrenheit. Okay. Now, one coded unit then equals 220 minus 180 divided by 2 gives us 20 degrees Fahrenheit. So 20 degrees Fahrenheit is, if you have +1 and -1 here, the 0 point will be equal to 100 degrees Fahrenheit. Then you go 20 degrees this way, it's 220. 20 degrees this way, it's 180. Okay, so that's your center point. And the value of 1 from 0 is 20 degrees Fahrenheit. It goes 20 this way, goes 20 that way. So that's what we're talking about here. So if the calculated step is change in A is going to be 0.5. Again, this is something that we just came up with as experimental designers. We have the authority and say we want to change A 0.5 units. What are we talking about 0.5? 0.5 is this coded value. So we're going to make a change. Remember, 20 was 1 unit. We're going to do half of that. So we're going to change not by 20 degrees, because that would be quite a ways. That's the full distance, from the center of the cube to the outside there. That's quite a ways for doing a change. So we decide we're only going to do it 0.5, which is 10. So when I do my ascending up, I'm going to go 10 at a time, 10 degrees at a time. That's what this is telling me. I want to do it 0.5. Again, it's just something as a designer I decided to do. Using my engineering knowledge, it seems like a pretty good way of doing it. So the natural step is, this is the coded data, the natural step is 0.5 times 20 is 10 degrees. We already calculated that in our head, but I did it there on the slide for you. This conversion is critical in practice because the experiment is conducted using actual process settings, degrees Fahrenheit, PSI, minutes, etc., whatever it ends up being, not the coded values. So I think that's pretty obvious why we had to do that. Okay, now now that I know that this is 0.65, remember where I got that from, right over here. That beta j divided by change in variable j is 0.65. And so that's where that came from. And change in B here is going to be 3 divided by 0.65, which is 4.62. Okay. And let's do the same thing with variable C here, 1.5 divided by 0.65. We're going to change that by 2.31. And so here it's all summarized for us. The factor A, I'm going to change at 10 degree Fahrenheit increments. B, I'm going to change at 4.62 psi increments. And C, I'm going to change at 2.31 minutes. And these are the values that I will use to determine how much I change all the variables as I go up and chasing the ascension to the top of the mountain. We had to have, what are we going to change it at? Well, we just gave you a rule that you can use to determine what those changes are. And they're pretty good. It's not anything overly magical about it. And if you feel you want to do something else, that's fine. But we're trying to find the steepest way up the mountain, and we're going to do it one step at a time. So the movement becomes A, 10 degrees, B, 4.62, C, 2.31. Our approximate. 2, 10, 4.62, and 2.31. Multiply those back by 0.65, and you get the coefficients again. So they're proportional to our coefficients. That's what I'm telling you. Exactly what Montgomery means by the path of steepest ascent is proportional to the signs and magnitudes of the regression coefficients. So we're trying to find the steepest slope using Montgomery's methodology, and that's what he recommends. And I know this can be complicated the first time you go through it. If you need to, go through it again, write it down on paper, work it out yourself until you feel comfortable and realize this is what Montgomery teaches us how to do it. And it's a good way of doing it. It's a good baseline to get started. You may tweak it a little bit here and there, depending on a few things, but I use it all the time. Illustration of response surface methodology concept. Typically, response surfaces are modeled using first-order approximation models before moving to a higher-order model in a sequential order to refine the estimate of the optimum conditions. That's a mouthful again. Okay, so typical response surfaces are modeled using first-order equations. There's no squared units in here. And you can create that with a fractional factorial design, a screening design, a full factorial DOE. It's your original block. You're finding out which coefficients or which variables are most important. That's why you run the initial experiment. Then we'll move on to higher order models in a sequential order as defined by going to have to go back here a ways, sorry. I didn't know it was this far. There it is right there. That's the sequential one we're talking about. Screening DOE, first order model. That's what we're doing. Find the most important factors. Create your first order equation. That's step one. That's what we're talking about back here. And then the second step, higher order model. The second is go to a higher order model. The second step is first to go ascend until you reach the basic region where the maximum is, and then do this higher order model in a sequential order to refine the estimate of the optimum conditions. Based on the geometry of the response surface, hilly or bumpy, a model might require multiple models of varying orders until an optimum is estimated. So you may have to experiment in this zone a little bit. It may take more than one experiment even. It just depends on how important it is, I guess. You may do your first experiment, say, yeah, this makes wonderful improvement, saves us $1 million a year, I'm happy with it, and you call it good. But you may say, I want to check to make sure there's not another optimum in here, and you may search a few other areas. For this reason, it is very important to test for evidence of quadratic, cubic, or higher levels of interaction during the analysis to ensure the optimum estimate has been sought correctly. Because our first cube assumed all those planes were linear. Well, what if they're not? Then you have error, and it may not be acceptable error. And that's what he's saying here. You need to check to see if there's any curvature in those planes. Well, that's what this methodology does for us. Illustration of the RSM concept. The sequential nature of the RSM is illustrated here. Here's our original design around operating conditions, that we're always operating our machine, but we don't know if it's the best one. It's just how it was set up, and we've been doing it ever since, but we're trying to do better. So we do an experiment, and we create our first order equation. Gives us the variables that are important. Then we take those variables that are important, find out how much we're going to change them incrementally as we climb up this mountain, and we change them incrementally until, okay, it's getting better, it's getting better, it's getting better, it's getting better. Maybe we're talking about throughput yield, and the yield just keeps getting better as we increase these variables. And then at some point, it starts going down. Well, we know the maximum is in this area somewhere. We know we're close, and we create this other equation, this other experiment here, okay, which is central composite design is what this is. And we're going to test, and we're going to start taking into account if those planes are not flat. And if it's not flat, we're going to correct it with the quadratic elements of the equation, the a squared, b squared, c squareds. And we're going to figure out what that radius is on that contour. And then from there, we'll find the maximum. If we're doing yield, we want maximum yield. So we're looking for the top of the curve. And this experiment will give us the top of the curve and tell us what the optimal settings are for within this range of the knowledge envelope anyway. Step 7, perform the central composite design. Remember, this is the one that's going to see how much we violated the assumption of a flat plane. It's going to check that, and it's going to correct it. And so it's going to be a much better estimator than we had before. Not only that, but it'll pick up on the curvature so we can find the optimal point. That's what response surface methodology is all about, finding the optimum. Remember, math does one thing for it. It allows us to see things. That's all that math does. It allows us to see things that we can't see with our eyes. And if we're real good with math, we can see things that no one else can see. And you can't solve a problem until you can see the problem. And when you watch data analysis people, you'll even hear them sometime looking at the computer and say, oh, I see. All right? And they do see it. Not with their physical eyes necessarily, but they see it with math. They see it with analytics. So if you get real good at this, it makes you very powerful because you're going to be able to solve problems that other people can't solve. And that makes you valuable. So hang in there. Don't give up. You'll get through this. In my opinion, the central composite design is one of the most elegant concepts in DOE. Once you understand why it was invented, the design itself becomes very logical. Why was CCD invented? Remember, central composite design. Imagine you just completed a 2x3 factorial experiment. You discover temperature matters, pressure matters, and time matters. Okay, what are we talking about here? You found out what? Imagine you just completed a 2x3 experiment. You discover temperature, pressure, and time matters. Okay, that's this first section here of the procedure. You find out which variables are important. That's what that first part is all about. You then perform the steepest ascent until you believe you chose the optimum. And that's where we figured out how much to change each of the variables. Now we're going to change each of those variables and start climbing the mountain. That's what they're talking about here. You then perform steepest ascent. And so now we're going up the hill. We have our first order equation. We got the variables that are important. We figured out how much to change them, and we're climbing the mountain. And that's what it's all about. Now you're here. You're somewhere around the peak. You know the optimum is somewhere nearby. The problem is that your first regression equation was this. There's no quadratic terms there. There's no squared. There's no a squared, b squared, or c squared. And when you do that, this is a linear regression equation. And in DOE, it means you are assuming the planes of your knowledge envelope is flat, not curved. That's all this can give you. It cannot give you the curvature. It's not capable of doing so. That equation describes the plane and does not show the peaks. We cannot find the optimum. It will not create this. It'll just create a flat plane there. But the real world isn't flat. So this equation doesn't work because most things aren't flat. Maybe over small sections they're flat, but you look at the whole surface, it's not going to work. The response surface curves. So the first order, all about linear. Second order, notice I have now x squared. Oh, I have square terms in here now. I may have a bunch of them. That's why it says add them together. So I have all the linear terms put together to describe it if it's straight. Then these quadratic terms, or whatever you want to call them, the x squared terms, it adds the curvature in here. So now it's a more accurate equation. And then this one here is summation of all of the interactions. All of the interactions right here. So that's what central composite design is, adding these x squareds in here to give curvature to this surface. Not just add curvature, but add curvature because that's what it really is. Okay. Now we may find out that the flat plane assumption is just fine, that there was no curvature anyway. But we want to be able to see if that's true or not. We'll check that later on. I'll show you how to check it. Okay, the second order model, here it is. Central composite design. Again, there's many designs here that can do this, but this is the most common. This is the one I tend to like the best, and most people do. But I'm going to go over the other ones so you know about them anyway. But here's the new equation. You have beta naught plus beta A times A plus beta B times B, the value of B, plus beta C times the value of C, plus beta AB times AB. These are interactions. If you listen to my other modules, you'll realize when I go A times B and A times C and B times C, these are the two-way interactions in a 2x3 full factorial design. And then, because it's a CCD model, central composite design model, it's also going to add these square terms. Beta AA times A squared, beta BB times B squared, plus beta times CC, C squared. Beta CC, C squared. Okay, there you go. But these elements of the equation right here, this A squared, B squared, C squared, those are the curvature terms. They're the ones that create the that create the curvature on this. Without them, there is no hill only a flat plane. Without these, you don't have this curvature. And notice now we're in the bottom of this sequential order thing here, because now we're fitting it. How does CCD estimate curvature? It's a good question. It adds new experimental points. Imagine a two-factor experiment. Factor gives, looks like a flat plane there. Only the corners. These 4 points define what? A plane. That's all it can give you. Now, you put a center point in. Oh, okay. Now, if the center point doesn't fall on a plane, if the center point does not fall on the plane, because you say if it's a plane, I can predict what that center point is, and it is not equal to that. There's error, if you will. It's deviating from the flat plane. Then it can use that dot to figure out what the curvature is. And if you put a few more dots in there, you can be even more confident. The center estimates pure error. N equals 8 or 9. This is the standard for most studies. So this center point, you may repeat it 8 or 9 times because I want to know the error involved. And it also comes up with the curvature, because you can predict what that value will be if there's no curvature. And if you find out it doesn't equal that, you know there's curvature. That's how it works. It's pretty simple, really. If the center response differs from the average of the 4 corners, you know the surface bends. So I use this example in a 2-dimensional so you can see it easier. And this was factor A. A when it's negative, A when it's positive. Okay, negative slope here. And then in DOEs, you do a center point. Why? Because you're determining if this is linear or not. And if you find out, you calculate this, which will be the average of these two, put it right here, and then you do a center point in your experiment, and it does not equal this, then you know it's not flat. It's not a flat line. This is the expected value if it was linear, but this is the observed value. Because it doesn't equal that, we know we have curvature. Now, I'm just talking about a straight line here because it's easier to visualize. But it's the same way with the planes in the in our model, in our knowledge envelope model, the cube, which comes from a 2x3 design, 2x3 design. So that is how we always go about determining if there is curvature. We figure out what it should be if it was straight, and then we run the experiment, and if it doesn't meet the expected value, and it's statistically significantly different, we know that there is curvature. And we're going to make up for that curvature with the squared terms of the equation. And we do that all the time in DOE. I did it in two dimensions there, but they'll do it in 3 dimensions for planes, but it's the same procedure. That's why you do a center point. And then we do these star points. They call them star points or axial points in CCD, Central Composite Design. And that kind of stretches everything out so that we can get a better picture of the curvature. So these stars, again called star points or axial points, these are called star points or axial points. So we're going outside our original design envelope because the curve may be peaked here, but it goes out here a ways further. We want to capture that with these axial points. It's kind of the anchor points for this. For this response surface. So hopefully that was helpful. Notice these axial points extend beyond the factorial cube. Here it is here in 3 dimensions. Here's the axial points. We're stepping outside our knowledge envelope. We're expanding our knowledge envelope is what we're doing. They extend beyond the factorial cube. Now the experiment can determine how sharply the response bends and where the optimum lies. It's pretty basic, but that's how it works. And once we figure out that curvature, we're pretty much there in figuring out where the optimum settings for a given machine is. Okay, let's look at the number of runs to run a central composite design. Now, first you have for 3 factors, full factorial, you have 2 to the 3rd power, you have 8 runs for that, DOE. Then you have center points to determine the error estimate. Remember, we're going to run the center point many times because we want to take the average, which will be closer to the true value, and we'll know the standard error, if you will, but they just call it pure error in this study. So you do quite a few reruns on that one. And the star points, you have 2 times k, and if we have 3, 2 times 3 is 6. So we're going to have 8 plus 9 is 16, 17, plus 6 is 23. That's on the high side. So we'll have 23 runs, or we could have 8 plus 5 plus 6 will give us 19 runs. So typically you'll have 19 runs, but those 19 points, you have 19 points on this surface here, response surface, and it helps us draw it all out and determine where the peak is at. Why are the star points outside the cube? Excellent question. Suppose your response looks like this. If you only measure inside the cube, many different curves fit the data. The star points stretch the experiment outward, outside your knowledge envelope, allowing the software to estimate better a squared, b squared, and c squared very accurately. It works very well. And in most cases, you'd say, you know, that isn't that many variables to do this. It's not that bad. It's very efficient with data. Now, you may decide to run replicates over here. Then, if you did, it would go up. But a lot of times you won't because you just want that first order equation. Finding the optimum. After fitting the quadratic equation, the surface looks like this. Okay, mathematically, you've got it figured out here. Notice I'm not going to do this by hand. I guess we could, but we're not going to. The software then calculates where the slope equals 0. Mathematically, the optimum occurs when the y slope and the b and the from a, b, and c slope all equal 0. Okay, and when they all equal 0, that's the optimum point on this surface. It solves these equations simultaneously. That point is predicted to be the maximum or minimum. All right, here we are. We're still on step 7 of performing the CCB Central Composite Design. You should feel fairly comfortable with all this now. Just do a little review before we move on. Example, suppose the fitted equation is 82 plus 6a plus 4b minus 3a squared, that's squared, minus 2b squared. So we have 2 squared terms here. Notice positive linear terms, that's these right here, 82, 6a, 4b, that's the linear terms. Negative squared terms, notice they're both negative. When you have both negative squared terms, you end up with a shape like this. Now, in a few slides down, I'm going to show you what a positive looks like, and a negative positive and a positive negative, and I'll show you all those. Remember, without the squared terms, the hill disappears and all you have is a plane. I know we've mentioned that before, but I just wanted to remind you of it one more time. So why is CCD, or Central Composite Design, so popular? Well, one thing, it's very efficient with data, because one experiment estimates main effects, 2-factor interactions, quadratic effects, curvature, and optimum settings. That's pretty amazing. For 20 or 30 data points to get all that information, that's phenomenal. No other classical DOE design provides so much information so efficiently. Now, this slide here, I'm just going to review the whole procedure again. Step 1, start with a full factorial design. Remember, you can also have a screening design. You can also have a fractional factorial design. You just need your first order equation to come out of this. I did 2 by 3 because it's a cube. It's easy to talk about. It's easy to visualize the informational envelope. Step 2, do the steepest ascent. Notice I did a cube around the whole steepest descent thing, but it's not within the operating range, your original operating range. You go outside that operating range and you do the ascent path. Remember, you can also do a descent path. Same procedure, only you're going down. So keep that in mind. Okay, so we covered that. So in summary, that's step 2. Step 3, add 6 axial star points and center points, which is the central composite design, of course. Notice we have replicates on that center point. That's very common. And once you finish that, then fit the response surface and find the optimum. So you take all the points. There's, a fair amount of points here, 20, 30 points, and you plot it out, and if you have a computer, it will graph it in for you from there. I mean, if you had to do it by hand, I guess you could plot it. That'd take you a while. But don't get me wrong, you can do this without a computer if you had to. Fortunately, there's plenty of softwares around here today. We can easily graph that with those data points. So that's a summary. A practical tip for applicable ASQ exams. One subtle point that is frequently tested on why CCD includes center points and star points. Center points primarily test for curvature and provide an estimate of pure experimental error. Okay, that's one of them. If you know these 3 things, you're going to get most of the test questions correct as it applies to CCD, or response surface methodology. Specifically, though, CCD. Factorial points estimate main effects and 2-factor interactions. Okay, and the star or axial points make it possible to estimate the quadratic a squared, b squared, c squared, etc. terms, which are essential for locating an optimum. Remember, these take into account the curvature. So if you have those 3 things down, you're going to get most of the CCD questions correct, if not all of them. If you remember these 3 purposes, you'll be able to answer any CCD-related exam question correctly. I hate to say all, but, it's going to help you a lot, is my point. Contour plots. Let's talk a little bit more about those. Contour plots and lines of constant response are used to help the experimenter understand the response surface for the purpose of more rapid converging on the optimum point. That's why we use contour plots, to find an optimum point. However, using the CCD, it gives good, you can predict values all over that surface. It's very good for that. You have enough data that we can do that. It's a really good information envelope. It covers a lot of things. Because the response surface may be rather hilly or bumpy, multiple maximums or minimums, or even saddle points might exist. We made it look pretty simple, right? It's not always that. There could be all kinds of things in this 3-dimensional surface. For this reason, determination of the starting operating conditions and the step sizes of the variables is critically important, because you can go too far and miss things. But it's kind of an engineering judgment type thing, because every phenomena is going to be different. And you may have to poke a few more holes out there, get a few more data points, depending on how important it is. But it doesn't take that many more data points. Maybe you did this area. Let me go back here. Maybe you did this area and you want to continue on up here. Well, do another CCD that goes over in this area or this area over here. It's not as if it's a one and done type thing. So keep in mind, sometimes you have to be patient to find the real optimum. And you should always be expanding your design envelope. Remember, in some industries, if you change something within the design envelope, you don't have to revalidate the process. So that gives you encouragement to keep increasing that. Let me read that again. Because the response surface may be rather hilly or bumpy, multiple maximums or minimums or even saddle points might exist. For this reason, determination of starting and operating conditions and the step sizes of the variables is critically important. Inherent risks. For example, if the starting operating conditions are somewhat off, the optimization technique may climb the wrong hill. and reach a less than desirable maximum. Similarly, if the step sizes of the variables are too large, the technique may step over the hill, climb the wrong hill, or converge again on a less than desirable maximum. And so my solution to that is go collect some more data. Don't be afraid to collect more data. Now, you may be on a constraint, time constraint, and you can only do the best you can do with the time given. You may be data constrained. There could be a lot of things, but for the most part, you can run some more data points and expand that surface a little bit more. It's always good to continually look to expand these things, expand your understanding. All right, with that being said, I told you I'd have a chart that would show you if the quadratic or the squared terms were negative, negative, or such as this one. And it gives the standard equation on all these, which are all pluses. But on this one, where it's shaped like this, beta AA must be less than 0 and beta BB must be less than 0. In other words, negative, negative. We already talked about that one. Okay, what if the squared terms are beta AA, which is a squared here, is greater than 0, so it's a positive number on one of the coefficients and a positive on the other one also. Beta BB is also greater than 0, so they're both positive. You end up with something like this. Okay, now this is a saddle point here. Sometimes they just test you on these response surface shapes and what they're called. So this is a saddle point, and the saddle point takes place where beta AA is greater than 0 and beta BB is less than 0. So you have a positive and a negative on your squared terms. That says that you have a saddle point. That's what it'll end up being. And if on this one, this is when beta AA, which is the a squared, beta AA squared, is less than 0, so a negative, and beta BB equals 0. Okay, then you end up with this, which they call a ridge line, if you will. This is a trough. They call this the trough. And this is when beta AA, the a squared coefficient, is greater than 0, and beta BB is equal to 0. So this one, the second coefficient squared, is 0, and this one is negative, and this one's positive. Now, no significant quadratic term when you build these equations. If your squared terms are statistically insignificant, it tells you there's no curvature, and you just have a plane. So anyway, hopefully that's helpful. As you imagine, they could ask a lot of test questions from this slide. So that's why I put it together so you can look these things up pretty quickly as needed. Would I expect you to memorize that? No, not really. I wouldn't. So response surface methods, minimum requirements. There must be at least as many experimental runs as there are coefficients to fit in the model. There must be at least 3 levels per factor so quadratic terms can be estimated. Attractive RSM features are it can predict well, and that is of course, a very powerful thing. It can predict well, especially the CC, Central Composite Design, CCD. It's very good at predicting. It may give you the maximum point, but it will also predict everything around it. So it is cost effective and lends well to sequential experimentation. In other words, once you figure out what the surface looks like, you can extend it out. Maybe this then comes down or something. Who knows what it does? But you can expand upon it. And I want you to make sure you remember that. Don't stop learning about your processes. I mean, sometimes you get so far out that you're never going to use that area. So I get that. You don't want to waste time and money. Okay. It cost effective and lend well to sequential experimentation, which we just went over. It provides sufficient information to allow for lack of fit testing. Okay, that's right. Checks for that curvature. It provides an estimate of the experimental error. Okay, this is very important also. Now you could use that to do confidence intervals or tolerance intervals, etc. It allows for blocking as part of the experiment. Yes, it does. And we're going to do an example problem here in a little bit, and you'll see we'll talk more about this blocking part. But I think the rest of this we've covered pretty well. Again, these are the types of optimization designs. We have central composite design. That's the one we've spent all our time on. And I think it's a good one to spend time on. It's my favorite. It just has so many advantages, and it doesn't take a lot of data. This is a face-centered cube design. So it's like the central composite design, only how far you extend out. By the way, how far you extend out from the center to this is called alpha. I know you're used to alpha risk and hypothesis tests, but alpha in CCD means the distance you bring out these star points outside, not just outside the cube, but out far from the center here. Now, face-centered cube, you bring all those star points into the face of the cube. So you're doing a test on the center of all the faces. So it's the same thing, only you're smashing it in. You're keeping within your original design envelope. But other than that, there's not a lot of difference there. You understand one, you should be able to understand the other one. The 3K full factorial design, 3K means 3 levels. Okay. It's so inefficient with data, I'd pretty much recommend that you never use it. This is so much better. I don't know why you'd ever use that. This is the Box Behnken design, and we talked about this a little earlier, and it has a different geometric form to it. It fits in that cube, but notice it doesn't do the corner points here. Okay, doesn't do the corner points. Sometimes those corner points are the furthest points away from the average here, and it may be dangerous, could be, may be extremely expensive, and so you may not want to test to those extremes. In that case, you may consider the Box Behnken design. It does have a disadvantage. It doesn't give you quite the ability to predict values throughout the informational envelope. It's not quite as powerful as the central composite design. But if these corner ones create a problem, a safety hazard, then definitely you'd want to go to this one. All right, rules of thumb for students. If your objective is identify the important factors, then do a 2x-K full factorial, fractional factorial, screening design, etc. If you want to detect curvature, 2K full factorial and replicated center points. Okay, you can detect curvature by doing center point testing on these. Okay, but it's going to be more of a flat plane if you just do 2K. Model curvature. So this detects curvature. Okay, your full factorial, if you do center points, it will detect curvature. But it's not going to optimize the process. You'll just know there's some curvature, but that's all you're going to know. It's not going to do a lot more than that. Oh, I have some curvature issues, but I don't know what it looks like. And model curvature and optimize the process, central composite design, CCD. That's where it is, model the curvature. Not detect curvature, but model it. Okay. Optimize, but cannot exceed operating limits. Okay, that's where we use the face-centered design, as I mentioned earlier. Optimize with fewer runs. Box Behnken is more efficient, has fewer data. I wouldn't call it less efficient because it runs fewer runs, but it doesn't give you as much predictive capability within the surface, response surface. Build the most complete 3-level mathematical model, 3K full factorial. Again, I'd pretty much take this one off the table. It's not efficient with data at all, and you're much better going with the CCD in my experience. So, but let's go over some of these. 3K factorial design. Remember, this is the one has a lot of dots in here. Does all the center points on the outer edge of the cube, and center of the face, and center of the cube itself. So you're covering a lot of areas here. And if it's full factorial, then you know, you're going to have all those planes that you did on the 2K design, but you're going to have more center points. It involves all combinations of K factors with 3 levels. K equals 3 factors, 27 combination runs. So 3 to the 3rd power is 27. And to the 4th power is 81. So you more than double your runs every time you add another variable. That's what I'm saying. It's not very efficient with data, and your company's probably not going to be happy if you use it because it's going to cost too much money. It could be easily noted that the number of runs far exceeds the number of coefficients to estimate in the quadratic model, especially when true when k is greater than 3. Okay, that's when you have a lot of data. Now, you may have enough data in your database, and you have a full set of data, and you have sensors on all your machines, and it's just growing this huge database that maybe you can do these without collecting any new data. That's something to think about. If you can, then why not? There may be some advantages to it. There is the option for fractional factorial designs. However, the confounding structure will add some confusion when applied. Yeah, some confusion is right. Okay. For 3 to 4 factors, this design will provide the necessary analysis. However, in the scheme of sequential testing, is not economical and therefore not encouraged. Okay, central composite design. I'm not going to spend a lot of time on this because that's where we've spent a lot of our time already. Notice I have my cube. The factorial points are the black dots. Notice they're on the corners of the cube. Those are called factorial points. Center points, the red one right in the center of the cube. The axial points. Remember, alpha is from the center to the axial point. If you read DOE books, sometimes they'll call that alpha. I wish they would have picked some other Greek symbol since alpha is used for many other things, but it is what it is. Okay, what's so great about this one? Very efficient designs, efficient with data. You get a lot of information for the data you invest in. Normal factorial designs, components, center points, additional axial points. It fits and works perfectly with the iterative testing. It can simply augment the 2-level designs with a handful of points. It can help circumvent the problems associated with running extreme corner points. Remember, these corners are the furthest away from the center, and then there's some processes you get too far away and it's not safe to run out there. And then you probably don't want to use that one. Here's the face-centered cube design. And the face-centered cube design is very much like this one. Again, only the alpha is 1. Here, 1 plus minus 1 here. It'd be 1 out here. Remember, that's the coded variable that I'm talking about. So you could say the face-centered cube design is an alpha of 1. And you can use the CCD with an alpha of 1, meaning 1 plus your plus and minus on your coded variables. Everything's going to be 1 away. And that's called face-centered. Central composite designs with alpha equals 1. There it is. 3 levels per factor rather than 5 as with the CCD. It is more rectangular versus spherical. It typically needs fewer center points than the regular CCD. When possible, the regular CCD should be utilized. Okay, the Box Behnken design. This one we haven't talked quite as much about. Remember, there's the shape of it. We've talked about the design envelope before. It can be a good alternative when the corner points are difficult to obtain. Clean design space with no axial points is less efficient compared to CCD when factors are more than 4 performing sequential designs. It can be thought of as a combination of 2-level factorial designs with a 3rd factor being held at the center. And so I put that out there for you. Note that this particular design in this example has 15 runs. And back to central composite design, CCD. The CCD allows unbiased estimation of the second-order functions of the form. Second order functions are where the x's are squared. Here, remember that's where we create the curvature with those terms. And it's not just, with this one, when you use CCD, it's not just finding the optimum, you can also predict all over that surface. That's what makes the CCD nice. All right, and so this one is just going to go compare Composite Design to Box Behnken Design. Just to give you a little more information, these are the two most popular designs, so I want to make sure you're comfortable with them. The primary objective of Central Composite Design: fit a complete quadratic model and optimize the response. Key word here, complete quadratic model. Box Behnken: fit a completed quadratic model with fewer experimental runs. That's its big advantage. Factor levels. 5 factor levels for CCD, which is alpha. Remember, alpha is the distance from the center to the axial points there. So alpha -1, 0 is the center point, +1. And of course, you have both positive and negative alpha for those axial points. What is it with Box Behnken Design? You'll have 3, which include -1, 0, and +1. So you're doing the plus minus thing like we do in regular DOE, but you're testing center points also. Okay. Star axial points, yes. No. Why do we like that? Because it kind of stretches us out a little bit, and it gives us a better model within our, especially within our operating range there, of curvature. So we can model it. It's a better model of that. Corner points, yes, we have them in the CCD. No, here. And sometimes that's an advantage, not doing corner points, because sometimes it's a safety concern. Sometimes it's a financial concern, those types of things. Center points, yes, we have center points in the CCD, Central Composite Design. And yes, we have center points in the Box Behnken Design, or BBD also. Rotatable, yes, with a proper alpha, that is correct. What does rotatable mean? Means it's a pretty good model that we can use to predict things off the optimum. So we can, all around it, that's why they call it rotatable. We can now predict things that happen all around this thing. That's, I think, pretty good for CCD. So yes, in center points. Oh, rotatable. Yes, with proper alpha, it does make it rotatable. Not quite so much on Box Behnken Designs. It's nearly rotatable, but not as good. Number of runs. There's more runs in the Central Composite Design in comparison to the Box Behnken Design. So if they're very expensive, you may want to look at this. Number of runs, more, fewer. We already talked about that. Prediction quality at boundaries, excellent. Excellent. And moderate at the boundaries. Remember how that thing went out and you have a boundary around it. Those can be kind of high risk to predict what the values are there, but with the CCD it works quite well. Not so good with the Box Behnken. Prediction quality near the center, they're excellent on both, because we usually run quite a few replicates on that center so we can find the pure error of the model. Advantages of Central Composite Design. I know I'm hitting this pretty hard. Why? Because I want you to be good at this. That's why I'm doing it. And sometimes you need to go over it more than once. So this is a kind of summary slides here, just to get you set up. Best CCD, Central Composite Design, which we've really been championing in this one. Best overall response surface design for industrial optimization. Estimates all main effects, interactions, and quadratic formulas, at least two-way interactions. Rotatable, giving nearly uniform prediction variance throughout the design space. That's wonderful. Excellent for locating the true optimum. Provides very good predictions near both the center and the boundaries of the design space. So you could make a good argument with the regulators, as long as you say within that surface that you should be able to change things without validating your process. That would be my argument anyway. widely supported by statistical software and extensively documented in the literature. Okay. In other words, it has a lot of credibility. Does that mean a lot? Yes. Particularly effective when the optimum may lie near the edges of the experimental region. We've already mentioned that. Disadvantages of CCD requires axial star points outside the original factorial region. So if you have problems testing at the corner points, you don't want to go out even further. So that's a disadvantage. Requires axial star points outside the original factorial region. Those star points may exceed safe operating limits, machine capability, regulatory limits, or material constraints. So those are things you need to worry about with this one. Requires more experimental runs than Box Behnken. Can be more expensive if experiments are costly, obviously. Advantages of Box Behnken design. Most efficient quadratic design when experimental cost is important. Requires fewer runs than the CCD. Central Composite Design. Never requires experiments outside the original factor limits. Okay. No experiments at the extreme cube corners, reducing risk. All design points remain within a practical operating region. Excellent prediction near the center of the design space, particularly useful when extreme operating conditions could damage equipment or create unsafe conditions. Disadvantages of the Behnken design does not include cube corners. So some ways that can be an advantage, some ways it can be a disadvantage. Less information about behavior near the edges of the design space. It doesn't do quite as well on that section of the response surface. If the optimum is near the corner, it may be missed or estimated less accurately. Not available for only 2 factors. Okay, slightly less robust than CCD for extrapolation near the boundaries. Now, we've said that in many different ways, but there it is again. Which one should you choose? Well, you need the most accurate response surface. You want to use CCD, Central Composite Design. Optimum may be near the edge. You want to use Central Composite Design. Need rotatability, meaning you can predict across that whole surface. Yeah, CCD. Experiments are expensive. Box Behnken cannot exceed operating limits. Box Behnken. Extreme settings are unsafe. Box Behnken. Want the fewest runs while fitting the quadratic model, especially when finding the optimum. It does pretty good with the optimum as long as the optimum is not near the edges. And Box Behnken for that one. RSM example. So now I'm going to run a quick example because I want to give you an idea of how this works in Minitab. And you may say, well, I don't have Minitab. I have Jump, for example. Okay, most of these softwares are not difficult to run. The difficult part is understanding what you're asking it to do. If you understand response surface methodology like is in here, you can go to any of those programs, you can find it, and you can figure it out. They're not as if they're impossible to use. They're only impossible to use when you don't know what you're doing. So, but you can also, I'm going to use Minitab in this one, but you can go to Jump and you can ask AI, for example, hey, I want to do response surface methodology. I want to use the CCD experiment type. Could you tell me the steps to use in Jump? And it will do pretty well for you. So don't give up on the rest of this if you're not using Minitab. You can always figure out how to do it, but at least it'll give you an example. A chemist, so here's the problem. A chemist is designing a process to control the temperature of a fluid under study. The cooling system uses resistive heating, okay, and forced air to cool down the fluid. The chemist is interested in determining how fast the fluid can be cooled from 95 degrees Celsius to 60 degrees Celsius. The following factors were selected based on prior experience with this process. So these are the factors: fan speed, fluid volume, ambient temperature, ambient altitude, and ambient humidity. And these are the levels. The high plus value will be 1200 RPMs, minus value will be 600. Remember, coded data. Fluid volume positive will be 125 milliliters, and the -1 will be 75. Ambient temperature, the positive will be 28.5, the negative will be 21.5. Ambient altitude will be 2,000 feet, and the positive will be 6,000 feet. They must have two factories at different places. Ambient humidity, 27.5 for negative, 62.5 for the positive setting. So there we have it. Note the chemist followed the CCD approach with 3 sequential steps. She decided to start with 2-level factorial design and augment the experiment with axial points if curvature exists. She conducted a half-fractional factorial design to get her first-order equation, remember. Design with 5 factors with 6 center points. That sounds pretty good. You could even use a screening design, perhaps, if you wanted to run fewer runs yet. But she conducted a half-fractional factorial design with 5 factors with 6 center points, which resulted in 21 runs, which totaled 2, 5 to the -1. That means it's fractional factorial. And that means you have 16 runs plus 6 center point runs. And so here's the design if you want to look at it. And remember, the reason they're running center points is to see if there's any curvature. You don't, all it's going to tell you at this point is, hey, there's curvature, but it's not going to really model it for you. All right, continued here. We will analyze the data together to assess the experiment, identifying significant factors using Minitab. We'll use Pareto charts, main effects charts, etc. to determine the significance of the factors. We will also examine the ANOVA table to determine the significance of the curvature. Okay, we're going to use Minitab. The ANOVA is going to pick up on curvature for us. I'll show you how that looks in a little bit. We will answer the question of, does the linear model first order approximation is appropriate to estimate the optimum conditions? Well, it will be if there's no curvature. Then if it's just flat planes, it's going to do just fine, most likely. So we plug it into Minitab, do the DOE. These are the factors that end up being important. Notice A factor, B factor, AB factor, and C factor. These are all the ones that are statistically significant. There's your critical statistic, 2.02 there. And notice, I think that's E or F. I'm not going to pass the eye test today. But anyway, all those in blue are statistically insignificant. And so very good. And it just tells you the same thing down here. And this is the ANOVA, though. We use the ANOVA, and it comes out and says curvature is 0.002. Okay, which means there is curvature. There is no curvature. That's a null hypothesis. The curvature equals 0, no change. And this is, 0.002, which is 0.2%. So it is statistically significantly different from a flat plane. So we do have curvature on this one. So that's important to know. The main effects show 0 on this one. Two-way interactions. Yeah. But this is the main one I'm looking for. There's curvature. Because now I can move on and use the CCD to figure out exactly what everything looks like. The center point is significant, and thus the system is nonlinear. And that's what we're talking about here, curvature. The center point is significant, thus the system is nonlinear. If the system was linear, we would have been able to create the response surface plot based on a linear model or first-order mathematical equation. For us to be able to create the second-order nonlinear model, we will have to run the axial portion of the CCD. Central Composite Design, remember. The CCD with axial points will aid in the modeling of the curvature of the system. We would do this either by, we start the experiment from scratch, okay, or we augment the axial points into the factorial design the chemist had already conducted. Let's start the experiment from scratch. Okay, and this is where you go in Minitab, Stats, where you usually go for this stuff, DOE, Response Surface, Create Response Surface Design. And that brings you to this Create Response Surface Design table here. And we notice it gives us two choices, Central Composite or Box Behnken. I went with Central Composite. You put in the number of variables. We had 5, remember. Second, you go into Designs. Third, there's you can pick whatever design you want here. 32 runs, 1 block. We're not going to use blocks on this one, although I'm going to talk about blocks here in a little bit. Center points, total 6, cubed 0, axial 0, default alpha 2. Okay, so if this is coded data, so we're going out 1, that'll be the face of the cube, then we're going to go out 1 more for our axial points. That's what that means. Notice it changes here for different designs. So it gives you a recommendation here. You usually want to stick with those. And so once you pick that, then you can go to, where's number 4 at? Go OK. And 5 is options. And randomize runs. It's probably smart. And then go OK. And of course you want to store the design in the worksheet. Then 7, you go OK. Then that will come up, Create Response Surface Design. We've already chosen the Central Composite Design. We have our variables. Now we're going to go into factors, go to axial points, and here's our factors. The 5 there, the low and high for each of those that we talked about earlier. Then 10, once you have that in, you can go OK. Remember, we're starting from scratch here. Note, select axial points and enter the name for the factor and their respective low and high values. Remember, you've already put in alpha, how far your axial points are going to be away from the center. It was 2. So just remember that. Here's our levels again. I just put them here to remind you where we're getting these from. All right, then it will create a CCD in Minitab. The following worksheet view is the output of the steps taken in the previous 2 slides. Remember, we told it to put it in the workbook, so it shows you all the runs here. I've broke them into 3 things. Red, draws 1 through 16 contain the factorial portion of the CCD. Okay, the cube, if you will. Only it's not a cube because there's 5 variables. Green rows, 17 through 26, contain the axial portion of the CCD, Central Composite Design, and the yellow contain the center points. So it gives us all 3 of those. And you can look over this if you'd like and make sure it makes sense to you. That's why I put it there. All right, augmenting factorial design. If we would like to augment the data to an existing DOE worksheet, adding additional axial point lines to the experiment that had already been entered in Minitab slide 24, or whichever slide that was, we would do the following: Stat, DOE, and Modify Design. Okay, and that would go here, and you can add axial points, default, etc., if you need to do that. Augmenting factorial design, and then it would give you this output. Run the axial points, part of the DOE. Once we run the experiment, we add the values for the axial points to the DOE sheet. We now have the ability to analyze the data and fit a quadratic model to better estimate the model of curvature. Remember, we've already determined that curvature exists. So that's why we're going to continue on here. After we combine the factorial and axial points into one experiment, we analyze the data by going to Stat, DOE, Response Surface, Analyze, Response Surface Design. And you go over here, select your experiment, go to Terms, Full Quadratic. That's usually what you want. And there's all your selected terms, all the interactions and the squared terms. Okay. And you go, okay, and here's what we have, estimated regression coefficients. It shows us that the constant is statistically significant. That's good. The speed is statistically significant. Notice the p-values are 0, 3 decimal points out anyway. Volume or velocity, temperature, though everything in green is significant. Speed, notice the p-value is 0.000. Okay. And so that's significant. And the speed volume interaction. So you have one quadratic or one squared term that's significant, one interaction that's significant, and three of the variables are significant. And notice the r squared is 98.03 and r squared adjusted is 93.91. And so there's a difference there. And what they're doing is they're penalizing you because you're throwing all these noise variables in that are statistically insignificant. When you do that, your r squared versus your r squared adjusted is going to be inflated, the difference between the two. We don't like that. We like to get r squared and r squared adjusted closer together. Well, it will become closer together if we just do this with the statistically significant coefficients, which is what we're going to do. And when we do that, you'll see these two will be very close to one another. Okay. Which tells you there's no phony baloney going on here. What you're trying to predict things with the other things that are statistically insignificant, which is somewhat insane to do. All right. And notice also the lack of fit here down at the bottom here is statistically insignificant. What does that mean? Okay, that's where it's going to get most of you in trouble. It's like, what does that mean? Is that good or bad? What it does is, well, let me show you what it is. What is lack of fit? So we're going to discuss what does this mean, lack of fit, and how do I interpret that p-value? Because it's kind of tricky. It's a little bit like the p-value on a normality plot. So if you're comfortable with that one, you'll be comfortable with this one. What is lack of fit? When we build an RSM model, response surface methodology model, we're trying to create an equation such as linear terms and a squared term here and an interaction term. Okay, so that's what we're trying to do. When we build an RSM model, we are trying to create this equation that contains all that information. The lack of fit test asks, does this equation fit the data well enough, or is there still systematic variation that the model failed to explain? If the answer is yes, the model fits. If the answer is no, then something important is missing from the model. Okay. So that's what we're doing with lack of fit. Do we have the right variables here to give us a good predictability power? Let's figure it out. Where does this test come from? Notice the bottom of your ANOVA table. Okay, right here, this is where it's coming from. It's an ANOVA table. The error term is divided into two parts. Error equals lack of fit and pure error. Remember what pure error is. I'm going to explain it here. Again, pure error comes from replicated runs. For example, suppose you ran the exact same settings 3 times. Speed and temperature, yield was 82. Again, you had speed and temperature at the same settings, you got 81. You had them at the same place, and you got 83. The difference between 81, 82, and 83 are simply random experimental variation. That's what we mean by that's pure error, the pure error of the experiment. You try to do your best, but there's always variation in these things. But that's the pure error, and that's what is in this equation. And so you have error due to that, which usually, it's kind of difficult. It is what it is there. And lack of fit. Well, we still haven't answered the question for lack of fit. Now suppose your fitted equation predicts y equals 76 under some conditions. But the average of those repeated experiments is actually 82. So this equation predicted this, but this is what it really was. That difference isn't random. We're telling you it's not random. It means the equation is missing something. Maybe these are the things that could be missing. These are very important. This would be a great ASQ question, by the way. The equation is missing something, maybe another interaction, another quadratic term, or perhaps the process isn't adequately prescribed by a quadratic model. That systematic difference is called lack of fit. Okay, so there you go. There's the lack of fit. Something changed here. It predicted, this is the predicted value, or the estimated value, expected value, if you will, and this is the observed value. And that's too far apart, and so we have already told you that this is significant. It isn't just random error. Okay, this systematic difference is called lack of fit. The hypothesis for lack of fit, this is where it'll start coming together for you. The hypothesis for lack of fit test is the null hypothesis, the model fits the data adequately. The alternative hypothesis is the model does not fit adequately. Notice these hypotheses are opposite of what many students would expect. That's why this gets confusing. Once you get this down, it all comes together. Because remember, that was statistically insignificant, which means I do not have enough evidence to reject the null hypothesis. And the null hypothesis says the model fits the data adequately. So this is actually a good thing. So there you go. And it's the same thing in normality plots. You want a p-value. If you're hoping for a normal distribution, you're hoping to see a high p-value because it's comparing your data to a normal distribution, and you want it to be statistically insignificant. That's why you want the high p-value. Tells you the data is normally distributed, highly likely. And so it's the same type of thing here. From your ANOVA table, the p-value, remember, equaled 0.183 using an alpha risk of 0.005, not to be used with the alpha of the CCD, unfortunately. 1.83 is greater, which is 18.3%, is greater than 5%. Therefore, H0, the model fits adequate. Alternative, the model does not fit. Fail to reject the null hypothesis. Meaning it's okay. The model fits the data adequately. That's a good thing. Interpretation, there is not enough statistical evidence to conclude that the model fails to fit the data. In other words, the remaining differences between the observed data and the fitted model are consistent with ordinary experimental error. That is exactly what we wanted. So that's a good thing. Why is this good? Most hypotheses tests hope for a small p-value. The lack of fit test is different. You actually want a high p-value because it means the model fits adequately. Rule of thumb, p-value greater than 5%, model adequately fits the data. Less than 5%, model does not adequately fit the data. You have enough evidence to reject the null hypothesis, which was the data fits. So it doesn't. The equation is missing something. Remember, I'm going to bring this up again, because these are the three things that most likely are missing if you have a low p-value. You may be missing out on an interaction, another quadratic term is out there somewhere, or perhaps the process isn't adequately described by a quadratic model. Okay, that systematic difference is called lack of fit. From the analysis, it is indicated that not all of the effects are required to adequately model the system behavior. To model the system, we only use the effects that are significant. And here we've already talked about those. Which ones were significant? I put an arrow to them again, just to know where we got that from. So now, to create the reduced model, we will only select significant terms. Now we go to Stat, DOE, Response Surface, Analyze, Response Surface Design. We go back, collect that again. Here are all the available terms, and we're just going to pick the ones that were statistically significant. Oh, what are we going to see now? We're going to see R squared and R squared adjusted are going to become closer together, or R and R adjusted are going to come closer together. Because now we're getting all the coefficients out that were statistically insignificant. We're throwing them away, so we're not going to get penalized with that R adjusted. Now, I want to also talk about a block. because somewhere in here it says, do you want to run blocks? There it is, include blocks in the model. Okay, let's explain what they mean by blocks. A block is simply a group of experimental runs that share some common condition that you cannot eliminate, but you don't want it to influence your conclusions in your experiment. Think of a block as a nuisance variable, something that changes between the groups of experiments, but is not one of the factors you're trying to optimize. So mathematically, you have the response equals the treatment effect plus the block effect plus random error. What we're going to do is we're going to wipe out this, just erase this from the equation, this block effect. That's why we do blocks. Let me explain more. The purpose of blocking is to remove variation caused by the nuisance variable so that the factor effects can be estimated more accurately. A simple example here. Suppose you're baking cookies to determine the best combination of oven temperature and baking time. Unfortunately, your oven only holds 4 trays, so you bake in the morning, run 1, run 2, run 3, and run 4. Then you take a break and you come back in the afternoon and you run 5, run 6, run 7, and run 8. Between morning and afternoon, the room temperature changes. The humidity changes. The oven characteristics may drift a little bit. Those differences aren't part of your experiment. You did not want to take that as part of the experiment. So you define morning as block 1 and afternoon as block 2. That's what this is for here. Include blocks. You can click on that and then you could do 1 and 2 blocks and define what those are. Okay? Now those differences aren't part of your experiment, so define block 1 and block 2. And when you do that, Minitab will it'll calculate the effects of that block, those blocks, but it'll eliminate it from the equation. All right. So here we have, notice the R value here. R squared adjusted is 94 point something percent. And the adjusted is 93.57%. So those two are very close together. That's always a good sign that you have a good solid equation, that you didn't use coefficients that were not statistically significant. So we like to see that. That's very good. That's an improvement. Remember it said 98. Yeah, it's 98, but it had some smoke in there. Okay. Coded coefficients. Okay, the second order RSM transfer function is given as cool time equals, and it gives you all your constants and coefficients over here for all those. And in the end, it will be cool time equals that constant minus 0.8413 times speed times 0.7034 times velocity plus 0.0449 times temperature. And here's our squared term, which was statistically significant, remember, speed times speed. Minus 0.6449 times speed square plus 0.5853 times volume times speed. That's the two-way interaction that was statistically significant. So it created this equation for us, and the equation looks nice. The original R squared looked pretty good. Remember, originally it was 98.03 and 93.91, but we've taken that down to 94 point something, and the adjusted is 93.57%. Very close to one another. So I wanted to show that and say, look how much closer we're together. That means our equation is much more efficient, and it's not blowing smoke, trying to use non-statistically significant variables to predict something. Okay, very good. RSM, create RSM contour and surface plots. Excellent. Now we get to throw in the quadratic stuff. The RSM function can now be used to create the surface and contour plots to visually describe the system, locate the regions of desirable conditions, simulate the system performance in nominal case, and estimate capability through Monte Carlo simulation. To create the contour plots in Minitab, go Stat, DOE, Response Surface, and that will take, and contour plots. And then you just say, what's the response? You can drop this down, pick the one you want. Of course, we want cooling time. And generate plots for all pairs of continuous variables on separate graphs. Makes it a little easier to read, so we chose that. You may choose something different, but that's one of the options. And then it will create these. And here's one on speed and velocity and cool down time. Okay. And notice on this, I'm just going to read the interpretation, but you can look at that. And cool time decreases non-linear as speed increases. How do you know it's non-linear? Because it's more narrow in some areas and wider in other areas on these contour plots. Cool time increases as volume increases. Cool time increases as volume increases. Okay. Volume increases up here. You can see time increases. Okay. Cool time decreases non-linearly as speed increases. Cool time increases as temperature increases. So take time to look at these graphs, get feeling comfortable with them. You can read my responses here. Make sure you feel comfortable. Okay, here's one. Cool time here's velocity, temperature, and contour plot tool time in seconds. Okay, notice that cool time increases linearly as volume and temperature increases. How do I know it's linear? Because these are uniform. They don't change the space between on the green. It's just parallel across there. That's how I know it's linear. Okay, now create the surface plots. You go to Stat, DOE, response surface, surface plot. Brings us back here, response cool time, we already had that. Generate plots for all pairs of continuous variables. Yes. And it'll create these. Remember, one was a plane. We knew that. And here are the other ones. So it gives you a three-dimensional plot for those various variables. What did we learn? Based on the analysis of these plots, we conclude that to reduce cool time, high fan speed, low volume, low ambient temperature, any humidity within the tested range is okay because it was statistically insignificant. But we only tested over a given range. If you go outside of that, we can't tell you on that one. We will need to specify what ranges we need specifically for these factors instead of high-low. All right, the objective of this example is to determine how fast the fluid can be cooled down, hence minimizing the cool time. We will now use the response optimizer. Okay, this is where it becomes nice. In Minitab to help us find the optimum settings. So it'll find where all those slopes are zero and tell you the optimum. Stat, DOE, response surface math, optimizer, and our goal is to minimize. We will try target here in a little bit because you'll see that this was going to create some problems, but we're going to try it. Okay, from the goal drop-down menu, there are multiple selections for the desired type of optimization. Based on the objective, we can select no optimization, minimize, target, or maximize, and we chose to minimize on this one. If it was standard deviation, of course, we'd want to minimize. So I just wanted to throw that in there that sometimes we want to minimize things. Okay, but right now we're going to do minimize and go okay, and it creates these graphs. We can tell from the optimization graph that the relationship between the cool time and the selected variables are linear for the volume and temperature and nonlinear for the speed. The optimum settings listed in the red brackets, there's our optimum settings right there. In the red brackets are provided here based on minimizing the response. However, the predictability Y value is a negative. We can modify the optimization technique to set target of 0. Because you can't have a negative time. That's what I mean. When we minimize, it goes below 0. Well, that makes no sense. So we probably need to go back and run it again and make it the target 0, not minimize. And we're going to do that. We can modify the optimization techniques and set target to 0, because that's physically bound by that, for the cool time, and consider that as the minimum we are looking for in this example. We'll repeat the optimization analysis and set the optimization method on the target to 0 seconds of the cool time to get the optimum settings. So this had some problems, so we're going to run it again. This time we're going to get target, and we're putting 0 as the target, 0 time. The optimum settings then are, once we change this, is speed 1200.9, volume 50, temperature 18, humidity any value within the tested range, altitude any value within the tested range, and we're good to go. And that's how you do it. It's not that bad. It really isn't. What do you need to do? You just need to go do it. You know, some people are afraid to try new things. Go try it. You'll see how easy it is, and then you'll be capable of using it as needed. Nothing is going to make up for the experience, but hopefully this lecture gets you closer to feeling comfortable of doing it. References: the Certified Six Sigma Master Black Belt Handbook, a wonderful publication, 2nd edition we used here, 2012, T.M. Kubiak, and this gentleman here, we can thank him for helping us. He helped me through his book to prepare for the ASQ Certified Six Sigma Master Black Belt exam. That was my book. Okay, and Design and Analysis of Experiment, 8th edition, 2012, Douglas C. Montgomery. Thank you, Douglas. We greatly appreciate it. What a wonderful man, a very intelligent man, and I would recommend his book to anyone, as I would for the Certified Six Sigma Master Black Belt Handbook. Okay, and then the major module contributor, the person that wrote a lot of this, was a Six Sigma Master Black Belt from 2022, Haig Abraham. And so thank you, Haig. We really appreciate that, all your help. It was great. Congratulations, you have almost completed this module. However, remember, you still need to complete that module exam. If you have any questions, please contact me at john.lee@alphatc.com. If you're interested in any of our classes, go to www.alphatc.com. We also have a DOE class there that if this was a bit too big of a step for you, you want to take our full DOE class. Congratulations, you have completed this module. I hope you have learned something new that will enhance your career. Thank you, and have a great day. Goodbye.